All right. Well, thank you very much for that kind introduction on behalf of myself, Nathan Savinelli, and my partners, Sung-Hoon or Josh Lee and Kimberly Lee. It's a true honor to be able to present to you today our recent work in front of the board and industry guests. Thank you for your time, and hopefully you enjoy this presentation. All right. There we go. So the problem we're trying to solve is one of integrating the human body with IoT systems and providing caregivers access to information that they wouldn't be able to normally see with just traditional alternative devices, wearable devices, etc. So the specific problem we're trying to solve: can cognitive stress be objectively measured with a wearable device? And we care about this because caregivers must effectively judge their patients' cognitive stress in dementia and long-term care environments. Alternative devices are highly limited. There's one extreme where devices are rigid and bulky and no longer wearable, like traditional ECG or hospital monitoring systems. They have excessive wires, and some of them also have codependencies like galvanic skin response as a temperature dependence that makes them not suited for long-term portable monitoring in different environments. And then on the other extreme, you have wearable devices that have reported low accuracy in clinical trials. So our hypotheses are that seismic chest vibrations, which we're terming SCG, can characterize the heart's mechanical function. What we're looking at is how the chest responds to each heartbeat, because the heart is a machine. It has a function similar to a pump, and we're looking at how that pump behaves in response to changes in cognitive state. And that gets into the second part of the hypothesis, that sympathetic neural activity can be effectively detected from changes in these cardiac mechanics. Third, we can design a soft sternal patch using stretchable or soft hybrid electronics that can capture these miniature SEGs, even though rigid alternatives have proven to be unable to do so. Finally, deep learning algorithms embedded in an Android app can classify SEG in real time and update caregivers of their patient's cognitive stress using a peripheral device. The design of our study was first to design this device, a Bluetooth device with an accelerometer, an ECG amplifier, and an optical sensor to get measures of blood flow and oxygen saturation similar to a finger probe but on the chest. Then we tuned the device mechanical properties to match the skin using, again, stretchable soft electronics. And we tested this platform then in vitro to see if the mechanics actually matched what we had, had identified as optimal mechanical properties. These signals were then assessed in vivo during controlled stress situations. We then designed advanced DSP techniques and deep learning to understand the SEG signal from a fundamental level, because this signal is not fully characterized in the literature. There's still a lot of uncertainty about what it specifically means. So we sought to use new attempts in particularly focusing on the DSP and then translating using existing deep learning techniques, but really hammering in on the DSP to understand what specifically does this seismic signal mean from a physiological perspective. And then we deployed all this DSP and deep learning into an Android app that could transmit notifications to the caregiver device. Just a quick overview of our device. It's a small, comfortable patch. Here's it on a patient or a subject's chest. It's very minimally obtrusive as opposed to some of those wire devices. And the mechanics are skin-like. We don't go into the actual mechanical assessment here, but we designed it such that the modulus, its bendability, and also in some cases stretchability is similar to what you'd see of the skin. Here's just a high-level functional overview of what the device and Android app are looking like. The next thing that we did was we tested these SEG signals in a clinical, not a full clinical trial, but with clinical technologies using echocardiography, which is ultrasound imaging of the heart. We're able to look at when the aortic valve is opening and not only see when it opens, but also the magnitude of the opening and also any sort of abnormalities in the opening. We can image something like this. Taking a 2D slice along that image, we can actually track the aortic valve in real time, and we can also track our SEG signal in real time and correlate each beat with things that are happening in the aorta. So what this showed, I won't get into it too much, it's a little bit more in depth, but what this showed basically is that we're able to gain a lot of insight about what's happening to the aorta based off of the seismic motions of the chest. So it's kind of a novel result. What we did then was we did in vivo experimentation, where the subjects would meditate, undergo stress, and then have normal activities. And we found that some of our advanced, I know I'm running a little bit out of time, but bear with me, please. We found that some of our advanced DSP techniques correlated well with stress, whereas some of the alternatives, their marketed alternatives, did not correlate well at all. We then designed a deep CNN with high accuracy in terms of detecting motion, relaxation, stress, different classes. We then implemented this into an IoT system with an Android app that had advanced DSP and machine learning, and sent that notification to a caregiver device. So in summary, we designed a system that can transmit data from the body that was previously hidden into IoT. And once it's in IoT, that can then be integrated into hospital systems. It can be integrated into at-home care. And we believe this sort of technology is the next step of what's going to be happening in the field of healthcare. I think this is the next big advancement. So I won't get into the next steps too much. You are welcome to ask questions about them. Thank you very much. I'm sorry if I went a little bit over the time, and please let me know if you have any additional questions. Thank you.